So how many iPhones will be sold? So we're looking in this lesson at transforming data. And we're going to start with the original data first, which is all iPhone sales during opening weekends. You can see here's the model, and then there's the year next to it. So first of all, I need to, I'm going to create a scatter plot, and we're going to use Statplet. So if you go to Statplet, make sure you go to two quantitative variables. Why? Well, there's the first quantitative variable. The year can count as a quantitative variable. And then units sold. So, but notice how, I could have 2007. It just would be kind of weird. So this is just the number of years after 2007, which is fine. It's just fine. So here we go. And we could do this on the calculator as well. And not too worried. Because odds of you having to create a plot are quite low. So I've got 7, 8, 9, 10, 11, 12, 13, 14, 15. Also, the reason I'm going to use the Statplet is it's a lot easier to do the residual plot on Statplet than it is on the calculator. My notes do have a section on how to do that if you are interested. So notice I put in the name and for the explanatory and response variable, and we begin our analysis. So there's my scatter plot. I'm going to go ahead and do a screen capture of that if I can. Give me 1 second. I'm going to have to get really big on this for a second, just so I can get my screen capture. There you are. Ignore what I'm doing for the moment. Hopefully this will work. And let me go back to normal size. There we go. Let's see if that worked. I didn't get yeah, that did work. All right. Sorry about that. I just couldn't see my screen capture button earlier. So I'm going to go ahead and size that down. And there's my scatter plot, right? Now, the next thing I'm going to do, so I'm probably going to end up doing that again, is let's go look at the residuals. So I'm going to scroll down and calculate the correlation. Don't really need to. Very nice correlation. So if you just based it on R, you would be tempted to say, oh, beautiful, beautiful. But let's go ahead and calculate the least squares regression line. I'm wondering if it's going to, let's do that in more detailed output because I'm curious. Yes, ooh. See, you might want to practice on this so you can actually get practice seeing what a computer output looks like. The main thing is there is our y-intercept and there is our slope. But that's not the point of this lesson. But I thought I'd show it to you while it's there. And also, do not do quadratic down here. It's tempting, but we're not doing that right now. I guess I could show it, actually. I take it back. For today's lesson, I'm going to do an exponential. And does it show exponential? So there's your exponential fit, right? And this is, let's go back to my original. There we go. Does it put the line back? Okay. So if we look at the residuals here, and I'm trying to figure out how to get my, oops, not showing. So I'm going to have to go mag again. Go off screen so I can capture my, ignore this. There we go. I have to go off screen so I can capture my plot of my residuals. And I'm coming back, I promise. Here I am. Okay, let's go put it in. Control V. All right, so here's the plot of my residuals, right? And the problem that we've got going on here is that we really do have a very curved pattern, all right? So if I look back at this Statplet for the regression, you can see there's the line, so it kind of goes. All right, so I'll try and draw what the original line looks like. Get a line. So it's kind of going somewhere around here, something like that, right? And so it's creating a residual pattern like this. So if I draw the residuals, let me draw them in a different color. There's your residual. So it's definitely a above, below, above, kind of below situation going on, right? So it's got a curved pattern to it. Why? Well, because this model really is, as I hinted earlier, it's more of an exponential shape. All right, so let me go ahead and catch up on here. So would you use a linear regression to model the data? Sketch a residual plot below to support your explanation. So we're going to say no. The residual plot shows a leftover pattern, U-pattern, U-shaped pattern, a linear model is not appropriate. All right. So what type of model did we think would work? Well, as we said before, the exponential. I could also do quadratic. I bet you a quadratic would look okay. So here, I'm going to just look at the correlations just to see. Not that they really apply. All right. Oh, there's your R squared is 0.9838. That's quadratic. That's not too bad either, because quadratic in a way kind of looks exponential. And then let's go, so 0.9838 and 0.97. Interesting. But we really do think it's exponential, because if you ever see those business plans, any DECA people out there, oh, we predict exponential growth. So that is the pattern we're seeing here, is that it's sort of actually this. So we're seeing more of a exponential growth, not a linear growth. Okay, so let's go ahead and write down exponential. And what does that look like? So exponential, let's look at the equation it brought up. The equation was, we'll just take it. There we go. So it's something in this form, okay? Now, I'm not going to worry about, usually I'm going to ignore, yeah, this. So this is the form. Let me see if I can just copy it. Probably won't copy very well. Actually, I'm going to just copy. Yeah. So we're going to just say the general form. So I'm going to just put an equation in here. Mrs. Overman's going on the fly. Y equals a, pretend that's an A, times b to the x. That is the exponential form right there. Let me change colors. Come on. Okay. So that's the exponential form. Let me also make it bigger. There we go. I'll make it a little bit bigger. There we go. So what is the inverse of this function? So I'm going to take a break and we're going to talk about inverses. Then I'm going to come back to these problems. So let's have a quick algebra review, because we're going to be doing inverses. So let's start with something we're more familiar with, which is the square root. So if I had square root of y hat, or predicted y, equals 2 plus 3x, predict y when x is 5. So I'm just going to take that 5 and put it in for the x right there, and I get 17. So, but I have square root of predicted y is 17. What is the inverse of square root? Because I'm trying to go backwards from the square root and undo it. Well, the inverse of the square root is squaring, right? Because if I told you, oh, I took the square root of a number is 5, you could probably tell me, oh, I took the square root of 25. So I just squared the 5. So when I square that, I get 289. Now let's go to logarithms, which you did in Algebra 2. Now I have log of y hat equals 2 plus 3x when x is 5. So I plug in the 5 again like I did before, and I get 17. Now, how do I undo a logarithm? Well, just in case you forgot from Algebra 2, what is a logarithm? So what I'd ask you to do is go in a calculator, go take the calculator, and we're going to take the logs of the following numbers. If you take the log of 1, you're going to get 0. If you take the log of 10, you're going to get 1. If you take the log of 100, you get 2. And if you take the log of 1,000, you get 3. Hopefully you're noticing a pattern, right? You're like, oh, it's kind of like the numbers of zeros. And where did the numbers of zeros come from? Well, these are powers of 10. So if I go log of 1 and rewrite it, so 1 is 10 to the 0. Oh, you see where the 0 pops out. 10 is 10 to the 1, and the 1 pops out. And then you have 100 is 10 squared, and the 2 pops out. And then you have that, oops, that's supposed to be 1,000. Let me change that to 1,000. Bad teacher. Oops, where are you? I want to put it. So that's supposed to be 1,000 right here. Yeah, just that last one. We'll pretend it's 1,000 because my pen's not working so well. That would be 10 cubed, and that would be 3. So log and 10 to the power are the opposites of each other. All right. So we have this, right? So what is the inverse of a logarithm? Well, we just said it's 10 to the power. So I'm going to do 10 to the log of y hat, or predicted y, is 10 to the 17, which gives me predicted y is 10 to the 17. Okay, so now we know that the inverse to this function is a logarithm. All right, so we're basically going to do our function equation. Let me go ahead and plug in the equation. We're going to take the log of both sides of our general equation. So it equals log of y equals log of a times b to the x. Oops, not that. Right? So that's our first equation. And then what we're going to do, I might actually do this on the side because we got more room on the side. So I'm going to just write it here. Okay. Oops. Ignore me. So, yes. So we're going to go from here to here. Okay. So we got log of y equals log of a to the bx. So we're going to take log of both sides. So what happens after I take log of both sides? Well, I'm going to have log of y. And then when you have a let me get back into the equation. That's what I meant to do. Log of y equals, when you have a product of two logs, you can take it separately, right? So log of b to the x. Okay. Then I can move the x out in front. All right. So log of y equals log of a plus x times log b. Oh, that's starting to look like a linear function. All right. So right here, that is your y-intercept. And then your slope, that's your, oops, sorry, not the x. X isn't the slope. The thing multiplying x is the slope. So that is your slope. All right. So now we have a linear form. So let's just go ahead, and it's like this is your new y, your transformed y. X is still x. And then we just have to have some logs for our slope. So now what we're going to do is we're going to actually transform the data. So we're going to take the log. Remember, this says log of y. So now I got to take the log of y. So just let me zoom this in just to make it a little bit easier for now. So I'm going to take the log of 0.5. All right. So log of 0.5 is negative 0.301. All right. I'll put this so you can read it better. All right. And I have my negative there. Yes. All right. And then I can take the log of the rest of the numbers. Log of 1, if you go to your calculator and punch in log of 1, it's 0. And then we also have 0 here. A wonderful space. Log of 1.7, 0.23. And then we have log of 4 is 0.60. And then log of 5 is 0.70. Log of 9 is 0.95. Log of 10 is 1 because 10 to the 1 is 10, right? And you're going backwards on log base 10. Log of 13 is 1.11. All right. So now I'm going to go ahead and punch this data into my Statlet. So we're going to go back here. We're going to edit our inputs. And instead of units sold, we're going to do log of units sold. And we'll plug in these numbers. Negative 0.301, 0, 0, 0.23, 0.60, 0.7. I don't really need the O when I'm punching in here. Keep your decimals when you're doing your analysis. Don't round too much, okay? So there's my new equation, and let's go ahead and do the correlation and the regression line. And you can see that now this looks a lot better. So let me go ahead. Sorry, I'm going to have to go off screen because my little screen capture disappeared off of here. I don't know where it went. So give me a sec. There it goes off screen, and then I have to go figure out where it is. So I'm going to capture the correlation plot that I got. All right. And let's go put it in our notes. And here we go. Control V. And let me go ahead and zoom out here now that I got my data in. Move this around. Okay, so there is my graph. All right. Go ahead and calculate the least squares regression line. So what I'm going to do, I'm going to go ahead and do the computer output because why not? There we go. So there's a computer output. I'm going to do a screen capture of this too, just so you can have it. So give me a sec. I'm going to have to go off screen again. I want you guys getting used to seeing these computer outputs because that's probably what you're going to see when on my test and the AP. So this is the output, right? So if we do it, the equation will be log of y hat. I'm just going to call it actually log of units sold, predicted units sold. Oh, it doesn't like that. Okay, I'm going to do this in regular text. It'll be fine. It'll be fine. Go away. Log of predicted units sold equals, and our intercept is negative 1.5427 plus 0.1836 times years after 2007. All right, and I'll put that down there. So that is your equation. All right. Okay, do you think the regression line is a good fit for the transform data? Why or why not? So we saw in the residual plot, there's a nice scatter. So let me go ahead and capture that, which means I'm going off screen again. Kind of sad I have to do that this time. Normally I don't. But it's fine. Yeah. Okay, there we go. And come back to normal. Come back to my notes. And there we go. Let's paste that in. There's my residual plot, which looks pretty darn good. All right, here I can zoom out a little bit. And yes, we would say yes. Yes, the residual plot shows no leftover pattern. There is an even scatter of residuals above and below the axis. All right, so now here's the fun part. This is probably the hardest thing. I don't know that you're going to have to do this, but this would be probably the hardest algebra we have to do. According to this model, how many iPhones will be sold in 2015? So I'm going to go ahead and write down, actually I'll just copy it. There we go. So we start with the equation, right? Oops. I thought I copied it, I guess. Control C. I just hit C, I didn't hit Control C. So what we're going to do is we are going to substitute in 15. So that's the years after 2015. And what we're going to get is, 1.16. So if you go negative 1.54, it's about 1.16. Okay. So that, how do we solve that? So essentially, we've got log of predicted units sold equals 1.16. Pretend I can type in the right numbers. Having keyboard problems today, apparently. If you want to do the inverse, remember how we talked about this? How do we solve this? We put a 10. So we use these as exponents on 10. Okay. And the cool thing is this goes off. So that means that predicted units sold equals 10, and I can actually do an exponent here, to the 1.16, get out of the exponent, which is 14.45 million iPhones. All right, so that's how you solve for that. Not going to be a huge part of your test or the AP exam, but it is fair game. So don't assume that you're done, all right? That you're like, oh, I don't have to know this. So those of you who are, going for those 5s, you should know how to do this. Going for a 4, probably not as critical. Okay, so calculate and interpret the residual for the actual number of phones sold in 2015. Well, we would say residual equals actual minus predicted. So, I added a J in there, no residual J. So it's going to be 13 minus 14.45. Remember, those were in millions, all right? Which is negative 1.45. So the actual number of phones sold in 2015 was 1.45 million. So which one was higher? The predicted. So the actual was lower. It was lower by 1.45 million below the prediction. Remember, you're probably tempted to, if you see a negative, you probably tend to say, it's under predicted, right? Actually, the prediction was higher. So always when you're trying to figure out under predicted or over predicted, just look at the actual and look at the predicted. Is the predicted higher than the actual? Okay, you over predicted. If it's lower than the actual, you under predicted. Okay, so now what are the important ideas? Well, I'm going to kind of just steal them out here and cheat. So, give me a sec. I always have to do a search for this tool that I'm looking for. So what were the big ideas from this activity? Let me go ahead and zoom out just a little bit more. There we go. Well, learning target 1 is that you understand that we can transform a couple of ways the original function. So if it's automatically linear to begin with, it's just x versus y. If it's a power function, you can do log of x versus log of y. Haven't done that too much, to be quite honest. Exponential, I think you're more likely to see an exponential function, which is x versus log of y. So what did we just do? We did an exponential function, all right? And then, let's see, we have the predictions, plug in x and solve for y. May need to undo a root or a log in order to get your y value, all right? So remember that if you have a log function, just put your 10 to the log and then 10 to this. These two are the inverses of each other, so it's like taking a square root and squaring, or squaring and then taking a square root. So they undo each other. If you have a natural log, we use e to the x, and that's actually quite common in actual life, although I'm not sure it's going to be a huge deal for us. So next part is we're going to check our understanding. I can zoom this in a little bit. There we go. So a party company specializes in creating balloon rooms, which are rooms that are filled with balloons from floor to whatever height is desired. The number of balloons needed to create a balloon room is a function of the length and width of the room as well as the desired height. Here's a scatter plot showing the number of balloons needed to fill rooms that have a similar amount of floor space. To various heights. Note the clear curved form. Because height is one-dimensional, number of balloons to fill the room, volume is three-dimensional. A power model of the form number of balloons equals A times height cubed should describe the relationship. Here's a scatter plot of the number of balloons versus height cubed. So now you can see this is definitely more linear here, right? In fact, I'll use a line. Where's my line? There we go. Definitely more linear, right? That looks pretty linear. So, because the transformation made the association roughly linear, we use computer software to perform a linear regression analysis of y equals the number of balloons versus the height cubed. All right. So, give the equation of the least squares regression line. So, always remember that your intercept is the first one, right? The constant. So that means you're going to take 45.008, multiply by a constant, basically 1. And then the height cubed, that's your x. So this is your, right here, there we go. So there's your, so there's your y-intercept. And then we'll say this is your slope, okay? So, but remember your x is height cubed. So normally I would say 10.809 times x plus that. By the way, it's probably good to practice. Just write these in order. Remember the intercept is first. So what is my y? My y is the number of balloons. Okay, so I'm going to say predicted number of balloons equals. Now I can actually just say number of balloons and draw that hat over it. But it's easier for me to type predicted. So I've got my slope, right? And that's going to be times height. And that's going to be raised to the third power. All right. So that's the equation. Okay. Suppose you want to fill a box with a height of 8 feet. So what would you do? So I would basically take this equation, right? And I would put 8 in there. So instead of height, I have 8. Okay. And if you substitute that in, you end up getting and there you go. So that is pretty much it. You just have to remember how to, luckily, since this is a power model in a way, so it's funny because it's say power and they have log, but you can actually have others. You're probably going, but wait, Mrs. Overman, that's not a linear regression. Well, we kind of hid the height cubed. We transformed it. If you ever take calculus and do U substitution, this might look familiar. All right, and that's it for now. I hope that was somewhat clear. And if you have questions, you're always welcome to bug me.